James, can we start?
Yes, I'd say let's go ahead and get started. Looks like everyone's joined in.
Okay, very good. Okay, welcome everyone. My name is Jun Li. I'm a faculty member in human genetics and computational medicine and bioinformatics. I'm also affiliated faculty member in MIDAS. Today, it's my great pleasure to introduce a speaker who is visiting us virtually from the School of Biomedical Informatics at the University of Texas Health Science Center at Houston, where Dr. Jiang is a Christopher Sarofim Family Professor and the Director of the Center of Secure Artificial Intelligence for Healthcare. His education includes a PhD in Computer Science from the Carnegie Mellon University. Prior to joining UTHealth in 2018, he was Associate Professor with tenure in the Department of Biomedical Informatics and UCSD. Among his many awards and accolades, I'll highlight a few. Dr. Jiang received the PI on multiple NIH grants and also career awards such as the CPRIT Rising Star and UT Stars Award. His trainees also received Best and Distinguished Paper Award from AMIA. Dr. Jiang is also one of the organizers of the MIDAS Genome Privacy competition. Today, his seminar has a title, Genomic Data Sharing, the Privacy Risk and Technical Mitigations. Welcome, Dr. Jiang. You may take it away.
All right, thank you. Thank you for inviting me. Really appreciate the opportunity. So today I'm going to talk about genomic data sharing, the privacy risk and technical mitigations. So I'm going to talk about mainly from the technical perspective to show what we can do in order to using technology as an enabler to mitigate some of the risks in genomic data sharing. So we're in this new era of genomic privacy as the data being increasingly collected and then more understanding have been accumulated. So as you see in this figure that there are a lot of related stories and news related to the use of genomic data. And then there are a lot of the popularities, not only in the research area, but also in the direct-to-consumer field. And then companies and then researchers are keen to get access to the genomic data. There's a national initiatives like All of Us, Million Veteran Program, and then international consortiums like GA4GH, trying to enable the access and then collection of large data. But at the same time, we also have the policies like GDPR, HIPAA, common rules to regulate the sharing of the data. So really this is a balance. We need to strike the right balance between the utility and then the privacy risk. So at the beginning, we have very little data on very few people. And then we have some data on some population. In the future, we'll have a lot of data on a lot of people. And then the more the data we get, and the more possibility we can do for research. However, that also comes with a bigger risk in terms of privacy. So today I'm going to talk about starting with these 4 blocks, the privacy risk in biomedical data, and then some important implication of the policy and the regulation. Then I'll talk about the formal models for secure and privacy preserving data sharing. Finally, I will talk about some of the ongoing community effort to improve healthcare data privacy and security. So I'll start with example, which is not genomic data related, which is on the metadata level. So this was conducted many years ago by my mentor, Dr. Latanya Sweeney, back at Carnegie Mellon University. What she showed is that even very simple data like a patient discharge information can lead to information disclosure. So a typical patient discharge information table have like a name, job, sex, age, disease. And then people usually think if we get rid of the explicit identifiers, then the data will look anonymous and so far can be shared. However, this is not the case because the unique and the sparsity in the data, for example, the job, gender, and then the age can be linked to external database like a voters registry. And so if you link these two databases, now you can see there's only one individual, dog, who is a 38 years old male, and the lawyer has hepatitis. And that's a unique record. So the unique link identifiability shows it's the disease risk of the patient. And these quality identifiers has been generalized, and then Dr. Sweeney has conducted a research and using that to review the identity of a Massachusetts governor by just using the three triplets of zip code, birthday, and gender. And she further showed that 63 to 87% of the US personnel can be estimated in a unique way using these triplets. And even without this kind of linkage, for example, if you have information regarding a cohort, for example, all the lawyer and who is male and 34 years old has HIV in a certain region, then I don't even need to link that to external database as long as I know, for example, my neighbor has those kind of attributes, then it's able to infer sensitive information from those records. And we can do even further on this type of information. For example, this is a work we received the EMIR Distinguished Paper Award several years ago. This was conducted on a public accessible HCAP data set from AHRQ. What this database allows you to query is you can send in different terms and then they give you the total counts of combination. If the count is below 10, then they replace that with a star. So ideally, they think then you cannot uniquely link this information to an individual. However, because you have the total sum of a column, then you can do some marginalization and then obtain some of the values of some of them. Even for those star values, when you replace that with a variable, then you can form a linear optimization problem. With slight trick, you can come up with the lower and upper bound of each of these values. So with that, you can actually quickly narrow down the search scope for each of the individual cells. Even though you cannot come up with unique numbers for certain cells, some of them you can infer that very easily. So for example, on this category, you can see there's only a single Native American within the age group of 65 to 84. Using that information, we were able to identify the information from the entire database. So now you can tell the ethnicity, you can tell the insurance type, residence, hospital stay, duration, the cost. Because for the mean of this information, there's only one individual, then the mean is just corresponding to that individual. So this actually exposed you can use inference attack to also obtain additional information. So on the clinical data set, there has been shown there's a lot of vulnerabilities. You can use the traits, family relationship, demographics, distribution of disease, even the duration, frequency of visit can be used to link. Well, in terms of the genomics, now we have an extra linkage. Now, not only based on this inference attack we showed early on, now you can combine this metadata with the genomic data to come up with even stronger attack models. So the genomic data privacy is in parallel. There's a number of studies showing how different type of models can use the aggregated statistics or individual variants to infer individual related sensitive information. So back at 2004, Ling and Altman published paper in Science showing 75 or more SNP is sufficient to uniquely identify a single individual. Mellin later showed in another JMIA paper that this type of information can be augmented to increase the re-identification risk. My colleague back at UCSD, GenomeWeb, published a paper in Science showing that you can use recreational database to search and then find ancestry information and then uniquely link to the surname of a large proportion of the population. And Dr. Arif Hamanchi, who is my current colleague at UTHealth, publishing a Nature Method paper showing you can use gene expression data and then link to the phenotypes and then backlink to the individual information to re-identify them. More than that, there are additional studies showing that you can use genomic data to reconstruct the 3D human faces. And another study showing that you can use the predicted human physical traits and demographic information to uniquely re-identify. And a later study shows that you can actually use weakly assembled information from the probability of age, skin color, eye, voice, landmarks, and facial information. Even though if each of them are at a low precision, when assembled, you can achieve very high accuracy in linking an individual. So those shows like the vulnerability of exposing the raw genomic data or even the aggregated level of information. In terms of the genomic clinics, actually, this is one of my favorite example. Warfarin is a drug for anticoagulant. So this is a very interesting drug because it's the dosage is depending on the genomic characteristic and the individual patient. For example, the patient of different age group, height and weight with different genome variant and then comorbidity history will have a different dosage. So there was a paper showing that because this model is constructed using logistic regression, so essentially if you obtain all the dosage information, you can actually reconstruct the weights on each of the field. And therefore, after you get enough sample, you can infer back the history and medical history, as well as the variants of the patient, just by looking at the dosage together with some non-identifiable information like age, height, and weight. So showing that a lot of the information seemingly anonymous actually can lead to sensitive information disclosure. And then facial information is another very vulnerable source when you link with genomic data. As we know that Mendelian disease, a lot of them are related to distorted face. So if you look at those kind of information, then you can link to the variant of the patient and therefore establish a connection and then use that to infer the information. And then a recent study showing that you can use MRI to reconstruct the face. And then together with genomic data, you can link patient in a highly accurate manner. And there are also studies showing that when you collaborate with other researchers, it is possible that through certain mechanism, they can infer your information through this collaboration. This is for image data, but as you can imagine, like if you're trying to construct a neural network with your collaborator, if the partner is honest, then they can use certain delegated mechanism to infer back the information you process and then uniquely identify the image or reconstructed image. If genomic data is involved, and this can also be reconstructed. And the membership inference attack model has been improved over the years and showing that you can use aggregated statistics during collaboration or even allele frequency can be used to identify membership. And there are ransomware attack models, and these days being observed more and more. And out of all the ransomware attack in 2020, and then if you look at the hospital, healthcare, and education, this proportion is going to be bigger and bigger, and it's doubled in the third quarter of 2020. And so a lot of attack has been applied to California and Texas. Well, with that said, I will go to some of the policy and the regulation framework in this area. So in the NIH world, NIH points to HIPAA, which stands for Health Insurance Portability and Accountability Act, for defining what is protected health information. So that explicitly defines a number of attributes, and then it has a definition on what can be reasonably exposed to allow individual to be identifiable. And then on top of that, there is also like a limited data and then de-identified data. So there are two ways you can ensure your data is de-identified. One is called expert determination. The other is called safe harbor. The expert determination is rarely used in practice because in a lot of scenarios, it's very hard to claim your data is fully de-identified without sufficient evidence of risk. So more used is this safe harbor rule. The safe harbor explicitly determines 18 elements, including name, geographical subdivision within a population less than 20,000, and dates except a year. And then there are a number of fields explicit identifying, for example, full face photo and compatible image, biometric identifier, including retina scan and fingerprint. Well, genomic, as we know, it's a gray area, right? As I showed earlier, like a 72 SNP is sufficient to uniquely identifying individual. Is that a biometric? It's a gray area, but I think it is because clearly it's stronger than a fingerprint. It can be used to uniquely identify an individual. And the common rule is the federal policy for protecting human subject. When we want to do research defined similar and HIPAA, then we need IRB review and then informed consent requirements to obtain the information from human subjects. And the common rule currently doesn't include genomic imaging data automatically as human subject. However, I think this is just a question of if and when, right? Because those information are highly identifiable. And then if those information are deemed as a PHI, then what is the right way to safeguard them while enabling us to conduct our research? And the EU has passed a more strict rule called GDPR. And then this is slightly different from what is being executed here under HIPAA. And so the informed consent framework is different. And then they also defines a different way to control the data. And the anonymization guidelines and the GDPR is different from the de-identification standard and the HIPAA. And it also requires explicit concern for scientific research, ensuring minimum data for studies. So if you're interested, we have ongoing work, which is still work in progress to compare common rule versus HIPAA and then GDPR in terms of their similarity and their differences. With this very brief introduction on the policy, I'm going to move into the formal technology model to safeguard and then protect genomic data sharing. So in terms of technology, actually, we have made significant progress over the years to ensure that we can use technology solution as enabler to allow multiple parties to work together. While not seeing the data, we can ensure that they can do certain tasks. For example, secure collaboration. So we have technology based on secure multi-party computation and homomorphic encryption to allow multiple partners to jointly work on encrypted data without directly accessing to the raw sequence or the raw data, so that we can ensure that the data privacy and the security is protected strictly and the technology. And then we can also ensure the output of the data is protected using technology like differential privacy. And between multiple institutions, sometimes we want to run advanced machine learning analysis. There's also federated learning mechanism while respecting privacy, so that we can ensure that data do not move outside your silo, but the models can be shared across collaborators. So I will start with the model that has been demonstrated on quite a good scalability on the Genome-wide association study by Dr. Bonnie Berger from MIT. So secure multi-party computation allows you to work with collaborators to jointly analyze or run a function without actually seeing the raw data. So let me give you an example how this is working. For example, if I want to get the salary of the sum of the salary of these three persons, but they don't want to tell me their individual salary, what is the way of doing this? So they throw two dice each, and then give the values to their neighbors. And then all they need to do is they add the value they receive and then minus the value they sent. And then they get a random share of their original inputs. So the salary is no longer the salary, it becomes a random value because it's perturbated by the dice, the random number they generated. And then you aggregate all these three together, you will find these values count out, right? And then you end up with the sum of x1 plus x2 plus x3, which is equivalent to the sum of the salary. So no one just give me the original salary, but obtain the final aggregate. So in terms of like a secure multi-party computation, the addition protocol can be easily executed in a way that like I introduced. If you want to do multiplication, it is slightly more involved because not only you need to share your decomposition of the value, you also need to share the decomposition of the multiplicates. So there's a technique called the beaver triplet. You can construct the beaver triplets offline and then use that to obtain the final multiplication. This respects the permutation rule. So no matter who started with this, you will end up with the same result. Based on these two basic arithmetic, the multiplication and the summation, you actually can construct the arbitrary arithmetic operations using series expansion and then other approximations. So essentially you can use these two to reconstruct the arbitrary function you want to do. Therefore, you can collaborate with other parties. And there has been a number of models like speeding up and scale up those kind of secure multi-party computation mechanisms. And then Bonnie's group has published studies showing that they can run on 500,000 population on million scale data using this secure multi-party computation so that the data is protected, but you can still conduct your analysis. They have also shown that you can do this DTI, the drug target study. So you can use this secure multi-party computation to enable pharmaceutical collaborations. But there are some like trade-offs of this mechanism. So this method is pretty fast, but each time if you want to design a function, you have to customize your protocol. So essentially it's kind of a garbled circuit. You need to generate optimization for your particular function to ensure that this is optimized for your computation. And then each party needs to be involved in this analysis. So it's not an outsourcing process. So essentially, this is good for like a one-time operation with a pre-specified objective function. Alternatively, there's another mechanism called homomorphic encryption. So this idea is slightly different. So this is, imagine if you have a like accumulation of a data repository and then you are not unsure what you want to run on top of it. One way to do is you encrypt the data and store in a repository. And then you can run your analysis when you have a function in mind. And therefore, you can run your encrypted function on encrypted data and finally obtain your encrypted outputs through this mechanism and obtain the result. So this is one of the 4 post-quantum safe technique as deemed by NIST. So this technology enables you to encrypt the data while still conduct analysis on the encrypted data and obtain the result. So essentially, the homomorphic encryption stands for same form. So which means you can operate in the same form on the plain text inputs and on the encrypted form, so to get exactly the same result. So addition, multiplication will be respected, and then you can get the data encrypted while you can still get the output respecting the original functionality. So in the real world, if you have input data, you after encrypt it becomes a very large like random looking bits, and then you operate on top of it, and then you can obtain your decrypted result back. So how is this done? So the state-of-art method is called learn with error. So essentially, this is to solve a linear system with equation. If you have a matrix multiply a vector equals to B multiplied by Q, this is a very easy to solve problem. However, if you add noise E here, then this reverse problem becomes NP hard, very, very hard. And actually, this is a notoriously hard problem, which even quantum computer cannot solve. So essentially here, the original protocol is learn with error, but in reality, we don't directly deal with matrix vector operation. We use a protocol called the ring learn with error to encode everything in a big polynomial. The reason of doing this is to ensure that we can leverage advanced FFT operations to save the time. So turns ON square complexity into n log n, because we can use the discrete version of the faster Fourier transformation to enable the parallelization of these operations. So with this mechanism, now you can conduct homomorphic operations. So the secret key is 1 and S. S is your secret. And then you have the set of the public key, which is A and B, and then operate onto this S and edit this additional noise to safeguard. So each time when you do an encryption operation, this noise will change. And this noisy message will mask your information. So it's not like hashing. Hashing, each time you hash the input, you will always get the same input. Here, whenever you operate each operation, even it's the same operation, you will get different outputs. So that now when you do the operation and then B and A plus M and 0, you get this CT, which when you use the secret key 1S, you can uniquely re-identify them, because this is just the reverse process. And then when you operate this in a grid, you can get rid of the added noise. There are several different styles of different quantum post-quantum safe encryption scheme. So one way is to add this noise ahead of your plain text you want to hide. So E is placed in the ring ahead of the plain text. Alternatively, you can also add this noise on top of back on top of the plain text. Therefore, you can use this to encrypt your message. When you see you want to multiply E1 and E2, this multiplication will respect your multiplication, while the added noise will be expanded. So there's a cost of doing this, because your ring has a fixed size. So you can only operate a limited number of times. And then if you exceed the size of the ring, then this information cannot be decrypted anymore. In the ring learn with error, the visual idea here is you generate like the encrypted data in a high dimensional letter space. And then each time when you operate, there's a slight noise gets added to the dots here because of the operation and the addition of the encryption bits. However, when you do the decryption, because we are modulized it in the ring, so it will go back to the end nodes of the letters. So the noise will not play a role. So in the end, you will recover exactly the same result as if you did not introduce this value. But people cannot decompose them while you do the operation. So the data is protected. So this small noise is used to propagate the information here. So we have a paper published in 2018 showing that this kind of technology now can be highly scalable. And then we evaluated our neural network using like public benchmark. So the MIST database, you see on this operation, we can achieve like 0.5 milliseconds per image. And this can be applied onto the genomic data and then operate on certain tasks like imputation or variant calling. And in terms of the output of the information, we also need to protect its privacy, because if you do not protect the information, I can infer the information. For example, if I ask everybody's aggregated salary, then when people left the room, then I ask the same question again. If you faithfully tell me the same information, even I use this secure protocol to obtain the result, all I need to do is to do a subtraction. Then I can infer the salary of the people who get out of the room, right? So you can use multiple queries or delegate design queries to infer individual information. Therefore, there's a need also to protect the output through the data analysis. So the privacy needs to be inserted to mask individual sensitive information so that the output is anonymous to an individual. So finally, we want to respect the utility while trying to provide the aggregated information being still useful. The idea here is we want to mask the individual's maximum influence on a function which you apply on a database. And then with and without a single individual will not change this function sufficiently so that this function is still usefully pulling information from your database while nobody can uniquely identify or get the information from this person based on the opt-in or opt-out from this database. So theoretically, this is conducted by adding a perturbation noise while you're running this function. Therefore, this is calibrated on the maximum degree of change for individual record being added or removed from your database. And then this is bounded by e to the epsilon, which epsilon is a privacy budget. Therefore, if you can bound these differences, individual's influence is masked by this perturbation noise. So by adding this calibrated noise to your query outputs, the information you get from this query function is masked. This is respecting a Laplacian distribution. It's a heavy tail distribution. Therefore, you cannot easily recover this information. But this also has a limit because the privacy has a budget. You cannot infinitely query this database because this is symmetric. If you do this infinity time, then you can still recover the shape and of a perturbated noise and recover it. So essentially, noise calibration is to adding the noise calibrated to the maximum degree of change of two databases by removing or adding one record, and then use that information with a perturbated noise calibrated by your budget to mask the information from your data. So using that, you can generate like a summary statistic, synthetic data, or generate machine learning models to be published to the public. If the data of your use is highly, highly sensitive, then from this privacy barrier, you can mitigate the risk. With this technology, actually, there are systems that are combining them and then build a realistic federated privacy preserving machine learning protocol. So a group in EPFL JP UBO has developed a system using homomorphic encryption, secure multi-party computation, and differential privacy to enable multiple parties can keep their own data while doing collaborative research. So each party owns their own key, and so nobody shares this. And then you can operate on the combined key to do your data analysis. And then in the end, when all of them are consented, then you can use the combined key to decrypt the result. I'll give some examples on what I've been talking. So this is one example on secure genomic testing. I don't know if you can see the screen. So this is based on the technology in homomorphic encryption. So the data are actually encrypted when they are deposited in the cloud. We run this genomic test, genetic screening, using homomorphic encryption. This takes longer than usual, as you can see, but underlying it's using a secure matrix operation to identify if a patient has any unique risk while the data is not exposed to the cloud or to the service provider. So you can see like with this, you can find certain genetic variant associated with certain risk, but the whole thing is operated in a homomorphic encrypted way without revealing the raw data to the service provider. So here is a polygenetic score of 0.21. And we also have some recent work using this federated data analysis framework to support COVID research. So I was co-leading a consortium with Dr. Yubo. It's called a SCORE, so Collective COVID-19 Research. So we're trying to pulling together data from more than 20 different centers from Europe and the US and Israel, trying to conduct the analysis so that we can enable federated learning and federated modeling without actually sharing the raw data to like respect the local policy while enable agile research. So as you can see, this is very similar to the I2B2 interface, but underlying we can conduct more than a counting query. We can study like a survival analysis, linear regression, logistic regression, and even run neural network by pulling the data from local sites. Actually, we are not pulling the data. We are pulling the aggregated and encrypted statistic and then distributed model to the local site to get the final combined global model. With that said, I would like to introduce some of the community effort right now ongoing. And then actually this is a very active research area because the data is becoming a bigger issue. So data sharing in the genomic world has drawn a lot of attention. However, on the upper layer, you can see all kinds of attack models has been developed. The King's genomic privacy, surname identification, face reconstruction. On the bottom, then you can see all kinds of defending models being developed. It's like chasing the tails. So whenever there's a new attack models being identified, then there's a new type of security or privacy technology being coming to defend them. And then there's additional modality of information drawn into the picture creates new vulnerability and more models come up to defend them. So there are also like a series of workshop and then competitions. I'm involved in this IDASH genomic privacy competition and workshop, and also as a co-organizer for the Genome Privacy workshop. Those are the two main streams of effort in the community, trying to work together and then push the front of genomic privacy research. So IDASH is one of the National Center for Biomedical Computing back in 2010. So this was one of the 8 NCBC at the time, the only one focusing on integrated data sharing. And then at that time, we were proposing 3 different types of model. The traditional way of utilizing the data to conduct exploratory research based on differential privacy, the remote way of conducting data in a secure enclave using homophilic encryption, or the collaborative way of conducting research based on secure multi-party computation. So over the years, we have been hosting the workshops together with AMIA and ASHG, rotating different cities. And then we have been engaged a big community of security and privacy researchers and trying to promote a common benchmark platform so that we set up the task together with genomic researchers and simplify them for the security researchers to tackle them. And then benchmark each year to see the performance improvement and see the feasibility of genomic security research. So starting with like a 2 country, 9 states, 33 registration, this community is quickly growing. And then in 2017, we have like more than 100 registration. And then in 2019, last year, we have more than 105 registered team from more than 20 countries. And then this is reported by Nature News and then GenomeWeb, sponsored by many industry and NIH partners. And we've been dealing with a number of interesting problems like genome sequence matching, secure GWAS, secure machine learning from encrypted data, secure genome imputation testing, and hardware-based solutions as well. As you can see, actually the improvement is significant. Over the time, we're doing our improvement is significant, and it has been showing that we can achieve a much faster operation several years ago than we can do recently. So we can do much faster operations these days, and then we can conduct faster sequence matching. And then most recently, we can operate on the genome imputation with more than 500 targets less than 3 seconds. So this year, actually, I'm going to host a workshop half an hour later. So we get 3 tracks, one on homophilic encryption, another on secure multi-party, and finally on differential privacy. We get a lot of teams and a lot of innovative solutions, and then teams come from everywhere all over the world. And then very exciting research. And if you're interested, here are the Zoom link. We are going to start at 4:30 Pacific time. So it's going to happen very soon. this is a very quick growing community, and I think we're dealing with a very, very important problem. I'm really happy to introduce some of the pilot work and some of the ongoing challenges we are facing. I'm looking forward to have the insight from my Michigan colleagues and then discuss with you. Thank you.
Thank you very much, Xiaoqian. That's really a tour de force. I much appreciate you going so quickly over such great content. I'd like to just now invite the attendees to ask questions. We still have more than 15 minutes.
Yes.
You can just unmute yourself or post in chat.
Yeah, I can do that.
Yeah. Maybe I'll start by asking you, Xiaoqian, to say a bit more about your drug repurposing work and how it relates to this privacy work.
Oh, okay. So that's a slightly different area of research. So on the drug repurposing work, I'm doing drug combination effect analysis. So essentially, I'm trying to look for synergistic effect of a drug from looking at large-scale electronic health record. So as we know, like drug-drug interactions sometimes lead to adverse events, but you can also have positive events, if these two drugs are have synergistic effect. So we're trying to use large-scale electronic health record to derive signals by doing counterfactual analysis together with the genetic network. So looking from both perspectives to jointly see the effect. It's not directly connected to the privacy research, but I know there are certain pharmaceutical companies are interested in looking at a genome sequence database. Previously, I worked with an institution which they have a lot of data. A genomic company, so the pharma company want to see their data, but they don't want share the data with the pharma company. On the other hand, the pharma company don't want to directly send a query because there could be a competitive issue for their adversaries. So we design some mechanisms and then instruct them how to defend those.
I see. So in that sense, it is related because your technologies is breaking down the barriers of sharing, and these pharma companies now will be a better frame of mind to start sharing. Right?
Yeah, it could be related. Yeah.
Yeah. Any other questions from the audience? Okay, let me read one. I saw one. Mm-hmm. Actually, Brian Bird, why don't you just ask it yourself if you can unmute yourself?
I can grant permissions for people to unmute themselves. So Brian Bird, Brian, let me get you unmuted here.
So Brian Bird, can you speak?
Just take 1 second. I said I have to find him in the list of attendees. There we go, Brian. You can unmute yourself.
Okay, thanks. Can you hear me now?
Yes.
Great. Nice to hear this presentation from you. It's really, as mentioned, a tour de force, and I really enjoyed writing this paper that I posted in the chat with you recently. My question for you is, when I go to I've gone to conferences like Pacific Symposium on Biocomputing, and one of the themes that comes up is people are concerned about the tension between the need to test attacks and the need to respect the terms of use of the data availability, which typically forbids attempts to re-identify. Right. And I'm curious to know, how does this play out in your work and in the work of your colleagues? What's permissible? What's ethical? How do you approach this?
Right. So we're trying to serve as an enabler role using technology actually to allow people to share more easily and then across the like a policy barrier, rather than saying that I'm showing you all these possible attack models, saying that the data is highly vulnerable. We know the data is highly vulnerable, but using certain privacy and security technology, you can actually achieve what you want to do without actually touching the raw data or expose those sensitive information. So I think the right to strike the right balance between the utility and then the privacy, we need to know what you are using this data for, right? So if we know you are analyzing this data for GWAS or analyzing this data for a certain type of functionality, then definitely there are ways to defend against potential attack models.
Okay, yeah. Thanks. So would you discourage people from trying to directly attack for the purposes of demonstration, or?
No, I think this, so I was thinking like there should be a way like allow like bioinformaticians or clinicians to easily use the tools we develop rather than like understanding all the complications behind it, because each domain is very different. So we're trying to build them so that you can use them as if like you're dealing with your original data analysis without like getting through all these details. So I think the goal is to make it easy and then usable rather than creating a barrier.
Sounds like a good goal. Thank you very much.
Thank you.
So Xiaoqian, when you talk about asset or privacy cost, is it explicitly monetized to a certain dollar amount, say for this amount of data and this much of attack, how much you need to spend to defend it?
Well, we didn't directly do that. And the way how we look at it is like data is like a personal asset, right? Individual data has a relatively low value, but when you aggregate the data, then it can create a larger value. That's why we collect a lot of individual data, and then the data like comes contributed from individual. So they delegate those trusts to researchers to use them to create a bigger social benefit. So we have a paper recently published showing our perspective. We think treating the medical data as a durable asset. It's not directly quantified as a money value, but we think like there are definitely values in this, and then a lot of new values are being generated as we know more and more. So we need to be very careful in defending this type of precious information being misused or abused by third party.
Very nice. Any other questions from the audience? I'd like you to comment on the people talking about these models have bias depending on which groups are represented, such as AI-based bias for different ethnic groups. How does that translate into your work?
Well, so this is related to like a reproducibility and then accessibility. So sometimes when people say the data is biased, it could mean like there are very few samples like the study subject. It could mean like the data is not accessible, therefore they cannot replicate the study. But sometimes the data has certain regulation or policy preventing it to be shared easily. What we are envisioning is, for example, if using our technology, you can replicate a study without actually directly getting access to the data, for example, in dbGaP, and then check whether the results match without pulling the raw data to see it. That could actually speed up and then ensure the scientific value of certain study while ensuring the privacy inherited in the data.
Let's see. In the beginning of your talk, you mentioned how the regulations such as HIPAA, it's a matter of when, not if, to be revised to reflect the new technology. But are you and the inventors been called upon frequently to discuss the revisions of the laws and regulations?
So we've been talking with program officers, and we are like this current changes in the genomic data sharing policy. I feel like there's a gray area, for example, like how genomic data is treated in research. But to us, it's pretty clear because there are a lot of attack models showing the data is uniquely identifiable. And this is a biometric data because it can be used to uniquely identify people like a fingerprint. I think it will eventually go there, and then the policy will define this as protected data. So we need to be prepared in terms of technology to protect those important and sensitive personal data.
I see. Thank you. Yeah, any other questions? Well, I want to thank you, Xiaoqian, for visiting us. Yeah.
Thank you, Jing, for inviting me. Yeah.
All right. Thank you. And you now have a few minutes back to your day. Hope to see you later, Xiaoqian.
Yeah, talk to you. Bye.
Good afternoon.
Thank you.
Awesome. Thank you, everybody.
Thank you.
Thank you, James.